Okay, in my first two videos, I had looked at cases with limits, and I completely forgot to cover what happens when you don't have limits. So for instance, in the first video, we had determined what a quarter of the area of an ellipse would be, and I believe it was, we had a 2/3, the integral from 0 to 3 of the square root of 9 minus x squared dx. So the main thing, we have the 2/3 out front, but we were really trying to figure out how do we integrate that, and we learned that we could do it by letting x equal 3 times sine theta. And then we could say, oh, dx must be 3 cosine theta, bring the d theta over to the right-hand side, and that would work. So we could substitute in for the dx. But then we also said, well, the limits are no longer 0 and 3. We have a theta here. When x is 0, we look back at what value of theta right here would make x equal to 0, and that would have to be a theta value of 0 because the sine of 0 is 0. And then we look at 3. When x is 3, what value of theta would make that true? Well, sine of pi over 2 is 3. So we rewrote the whole integral as the integral from theta equals 0 to pi over 2. I guess there was still the 2/3 out there. And then we had the square root of 9 minus 9 sine squared of theta. And hopefully you recall that that simplified greatly. And then the dx could be replaced by 3 cosine theta d theta. And we were able to simplify. And because we have limits for theta, we could get a numerical answer for this. We never had to go back to x. But let's consider what would happen if we did not have the limits. I'm going to drop the 2/3 now. I'm just going to simply look at the problem. What is the integral of the square root of 9 minus x squared with respect to x? So we will still use the same substitution. So I'll just box that in. I don't need to write that over again. So this equals the square integral of the square root of 9 minus 9 sine squared of theta times, I'll put it all in parentheses, 3 cosine theta d theta. Okay, so now we can draw a factor of 3 out of the square root, and we have another factor of 3, so that brings a 9 out to the front. When we take all the constants out, we're left with the square root of 1 minus sine squared of theta times cosine theta d theta. Hopefully you remember that the 1 minus sine squared is cosine squared, and we take the square root of that. So we end up with 9 times the integral of cosine theta times the second cosine theta, so that's a cosine squared of theta d theta. And this brings us into a trigonometric integral problem, where we can say, this is, I'll bring the 2 out front. We can say this is 1 plus the cosine of 2 theta, since we're working with even powers here. So it's really 1 plus cosine 2 theta over 2, but I drew the factor of 2 out to the front. And then we'll have a 9/2. And then we can take antiderivatives of this, and we have theta plus 1/2 sine of 2 theta using the quick chain. And then we should tack on a plus c at the end. We could obviously distribute the 9/2, but here is where we're a little bit stuck, all right? My answer should not have theta in it or 2 theta in it, as a matter of fact. And the reason why is because the problem didn't start with thetas. The problem was all written in terms of x's. So our antiderivative has to be in terms of x's. Well, here's where we use the original substitution to geometrically figure out what must be true about theta and 2 theta, or sine of 2 theta, in order to get back to having x's. Right, so I can draw a triangle based on the sine of theta must equal x over 3 if x equals 3 sine theta. All right, So I can draw a triangle here, a right triangle, since it's the we're doing trigonometry, so it's all about right triangles. We have an angle theta, all right? And if you recall, the sine is the opposite over the hypotenuse. So we can take the x and put that on the opposite side from the angle, and we can put a 3 on the hypotenuse. And then using the Pythagorean theorem, we know that whatever goes on this horizontal leg, when we square it and add it to the x squared, we better get a 9. Okay, so what would work? 9 minus x squared. If you wish, you can just go to a squared plus b squared equals c squared, fill in x squared plus the unknown leg must equal 9, and you'll get to the same point that I just got to right there. So let's now figure out what we need to figure out, right? So from this triangle, we can figure out all kinds of things, all right? We could figure out, first of all, since the sine of theta is x over 3, our answer has a theta in it. So we can figure out that theta must be the inverse sine of x over 3. So now notice we have theta in terms of x, right? We could also figure out, okay, we know that the sine of theta is x over 3, but we could figure out what the cosine of theta is. The cosine of theta is, looks like square root of 9 minus x squared over 3. We could figure out the tangent of theta. It's not needed in this problem, but we could figure out that the tangent of theta is x over the square root of 9 minus x squared. Don't worry about rationalizing the denominator. And then if we know the sine, the cosine, and the tangent, we could find their reciprocals, right? We also could figure out what the sine of 2 theta is. You should recall that the sine of 2 theta is a trig identity, the double angle identity. You may not remember what it is, but remember in the back of the textbook, all the trig identities are lined up. It ends up being 2 times the sine of theta times the cosine of theta. That means we can rewrite our answer as 9/2 times theta plus the half and the 2 cancels, so then we just have sine theta cosine theta plus c, and then we can go over to the triangle and we can pick out 9/2. Theta would be the inverse sine of x over 3 plus, and then we can put in sine of theta, that is just x over 3, times the cosine of theta, which would be the square root of 9 minus x squared over 3. And then we just have to tack on the plus c. Obviously, this will simplify. If we make a denominator of 9, I'll leave that to you. To do that, we could distribute the 9/2, and we would probably get a slightly better looking answer. Let me just do that. So if we distribute the 9/2 and we simplify, we'll have 9/2 of the inverse sine of x over 3 plus the 9's will cancel, so we'll have 1/2 x times the square root of 9 minus x squared plus c. So that is actually the antiderivative in terms of x, which you would be required to do. All right. Now, there are other problems in the homework that might look more like, let's look at this one, the integral of 1 over x squared times the square root of 9 minus x squared. So you'll notice, integrated with respect to x, you'll notice the radical is the same. So what will happen after you do some canceling of things, you will end up with simply something that looks like this, 1 over sine squared theta d theta. All right. And you probably, hopefully recognize that's on the memory list if you rewrite it this way. So cosecant squared is the derivative of a cotangent. Well, the negative derivative of that. So the antiderivative must be negative cotangent of theta plus c. But once again, the problem started in terms of x, and we have a theta, so we need to get the theta out of there. So you would look at the triangle that we had before, and we've already determined what the tangent ratio is from that triangle. So while we didn't use that in the example we had just had, we would use that here, and the cotangent is the reciprocal of the tangent. So we could say this is equal to negative square root of 9 minus x squared over x plus c as a final answer. So it really comes down to being able to create the triangle based on what you substituted that x equals 3 sine theta. So drawing a triangle that would illustrate that relationship, and then pulling off the appropriate trig functions. And then occasionally you might have something like a double angle formula that you need to pull out in order to solve the problem. With these in mind, you then can answer the questions that don't have limits of integration.